So at the start of this video, I would like to briefly review summation notation. I'm hoping you've seen this in your previous classes. This is the worst thing about teaching over a video is that you can't is that none of you are able to answer me. So let's recall summation notation. So how this works is we write the Greek letter sigma. That is Greek for S, which stands for sum. So you write sum from K equals any number you want to start with. K equals M to N. F of K, where F is any function, any mathematical function, any mathematical expression. And what that means is you write F of M, then you add to that F of M plus 1, and then you add to that F of M plus 2, and you keep on going. And eventually you get to F of N minus 1, and finally you stop at F of N. And if you like, I can write this in pseudocode. But you start with a variable, this block of pseudocode. So we're going to write S equals 0, and then for K equals M up to N. We're going to let S equal S, and then we'll add to it F of K. Close our for loop, and then just return S. And there's some sort of programming language where that comes out to this sum. So let's have a couple of examples of this. So let's sum from K equals 0 to 5 of K squared. Then I would write 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Or the sum from K equals 3 to 6 of 1 over K is 1/3 plus 1/4 plus 1/5 plus 1/6. And you can simplify those, but that's really not at the point. The point is this notation with the big sigma, it lets us write sums very efficiently. And I will mention that sums have a lot of nice properties. So in particular, it has many of the same properties as integrals. So, for example, the sum from K equals M to N of F of K plus G of K. You can break up a sum over summation just like you can break up an integral. And you can pull constants out of sums exactly the way you can pull constants out of integrals. That's a very abstract bunch of fractions, bunch of formulas, so let me give you a couple of examples, and you can see how this works. So we'll write this expression, sum from k equals 3 to 5, because I don't feel like writing too many terms. 2k squared plus 3 over k. That's 2 times 3 squared. We'll plug in 3 for k. And then we add to that 2 times 4 squared and a 3 over 4. And then a 2 times 5 squared and a 3 over 5. And then we can group some similar terms and pull a term out. We're going to group the squared terms, the 3 squared and the 4 squared and the 5 squared, and I'll pull the 2 out. I trust all of you took algebra, passed algebra, so I think if you need to pause the video and stare at this for a moment, you can, but you should be able to convince yourself that this equal sign is a true equal sign, that these two expressions are equal to each other. And then we can turn this back into summation notation. And you see we broke the sum up over the plus sign and we pulled the constants out, just like you can do it with integrals. If you're a mathematician, you think of that in the other order. It's a lot easier to convince yourself from first principles that this stuff should work with sums. And then you use the fact that it works with sums to convince yourself that it works with integrals. That's really what you do if you were trying to convince yourself of these facts from the beginning. But in my experience at this point in your college career, most students are a lot more familiar with sums than they are with integrals, and other way around, are a lot more familiar with integrals than they are with sums, and consequently, if I say you can break up sums and pull out constants just like you can with integrals, that actually does seem to turn out to be a useful thing to say. So in this video, we are going to discuss the binomial theorem and, time permitting, the multinomial theorem. So to discuss this, we're going to start with an example of a counting problem, which I think will provide us some useful motivation. So first off, we're going to ask how many six-character license plates are there? No restrictions. You can use letters or numbers in any order. Any number of them, any number of repeats, whatever you want. So the solution to this one, of course, or so we all know, is there are 36 options, 26 letters plus 10 digits. We're assuming you can tell 0 and O apart, and then so that's 36 options for the first character, 36 options for the second character, and so on. That's 26 plus 10 to the 6th power. All right. So next question we're going to ask, how many of those license plates are going to have exactly, let's say, 2 digits. That is, 2 of the characters are digits numbers 0 through 9, and the other 4 are letters. And the solution to that one is there are a number of ways that you can do this, but one way to think about it is first you're going to choose which of those letters, which of your 6 characters are going to be the digits, and then you multiply by 10 squared to choose what the 2 digits are. 10 choices for your first digit, 10 choices for your second digit, and then 26 to the 4th. That's 26 choices for your first letter, 26 choices for your second letter, 26 choices for your third letter, 26 choices for your fourth letter. We have, in fact, done this problem before, so I'm not going to go into it in great detail. All right, and so similarly, how many license plates with 5 digits? And the solution to that one is first you pick which of your 5 characters are going to be digits, and then you have 10 to the 5th options for your 5 digits and 26 options for your 1 letter. And I'm going to label that 26 to the 1st. And final example, how many with no digits? And the solution to that one well, the solution is you've got 6 characters and they're all letters, so there are just 26 to the 6th letters in a row. But we would like that to look a little bit more like the numbers we've got above. So I want a 10 to some power, but I don't actually want to change my answer at all. I just want 10 to the 6. So I'm going to write 10 to the 0 here. 10 to the 0 is 1, so I'm just multiplying my answer by 1. I'm not actually changing it anyway. And then notice that I had a 6 choose 2 for for my first answer when I had 2 digits, I had a 6 choose 5 when I had 5 digits. Do I have a 6 choose 0 when I have 0 digits? Well, let's notice this is true because 6 choose 0, what that is 6 factorial divided by 0 factorial, 6 minus 0 factorial. The two 6 factorials cancel out. 6 minus 0 factorial is 6 factorial, and we're left with 1 over 0 factorial. 0 factorial is 1, and so we just get a 1. And similarly, the number with all digits, that is going to be just 10 to the 6th, because we've got to 10 digits, first, second, third, and then we multiply by 26 to the 0th power, and then 6 choose 6. 6 choose 6, that's 6 factorial divided by 6 factorial, which is 1. And then there's a 6 minus 6 factorial, another 0 factorial. So I'm not going to write that out. I'll leave it to you to check that this is in fact 6 choose 6 is in fact 1. But that should not surprise you if you've got 6 If you've got 6 cookies, there's only one way to choose 6 of the cookies, and that's take all of them. All right. So now the point of the binomial theorem is we're going to take these two answers and put them together. So if you want to know the total number of ways to make a license plate with 6 digits, that's 10 plus 26 to the 6th. But that is also what you get when you add up the number. So that's the total number of license plates. But a license plate is always going to have some number of digits. It's going to have either 0, 1, 2, 3, 4, 5, or 6 digits. So we're going to have 6 choose 0, 10 to the 0, 26 to the 6th, and then 6 choose 1, 10 to the 1, 26 to the 5th. And then we just keep going. And so we've got this very nice pattern. And then all we really have to do is put the pattern into summation notation. So we'll sum from k equals 0 to 6, and then our summand is 6, choose k, and then there is a 10 to the k and a 26 to the power of 6 minus k. And so this is coming just from the fact that there are two different ways to compute the number of license plates that you can make with our alphabet, which has 26 letters and 10 digits. It's 10 plus 26 to the 6th power, because you've got 6 characters and each of them have 10 plus 26 options. Or you can compute the number that are all letters, no digits, compute the number with 1 digit, the number with 2, 3, 4, 5, or 6 digits, and then just add them all up. So the binomial theorem, so there is nothing special about the number 6. You could do the same thing with 7, 8, 9, 10 digits. You just have to go from 0 to 7, 8, 9, 10 in your sum, and you'd have 7, 8, 9, 10 choose k in your computation of how many license plates with k digits. And there is something special about 10. It's the number of digits in our numbering system. There is something special about 26. It's the number of letters in our alphabet. But for the purpose of this problem, there's nothing special about 10 and 26. You could do the same thing with an alien alphabet or a non-Latin alphabet with any number of digits, any number of letters you could use, and you could make this exact same argument. So this is true for any numbers. X plus y to the n is always going to equal the sum from k equals 0 to the n of n choose k times x to the k times y to the n minus k. And this is true if n is a non-negative integer. That's sort of all you need. If x and y are also integers, you can make a license plate type argument explaining why this is true. But as it happens, this is also true if x and y are, in fact, any real numbers. This works for x and y as fractions. This will even work if x and y are something weird like square matrices. Anytime you can add and multiply, you can put together an argument for why this is going to work. And let me show you an example of the kind of problem which you answer with the binomial theorem. So here is the question. What is the coefficient of x to the 5th in the expression 3 plus 2x to the power of 9? That is, if I take 3 plus 2x to the 9th power and I expand it out, I FOIL it out 9 times, which is annoying, but can be done, although that's starting to get into the point where you're better off writing a computer program to do it for you than to try to do the multiplication by hand. So the question is, what do you get? And the answer is not actually all that hard to compute. You can actually figure this out just from the binomial theorem. 3 plus 2x to the 9th power. That is the same as 2x plus 3 to the 9th power, and I think that will make your life a little bit easier. That's the sum from k equals 0 to our n in the binomial theorem, this n here is the same as this 9 here. So we sum from k equals 0 to 9, not from k equals 0 to n. And then again, our n choose k turns into a 9 choose k. The binomial theorem has an x in it. We've actually got a 2x here. So what we're going to do is we're not going to, where the binomial theorem says x, we're going to write 2x to the k. And then where the binomial theorem has a y, we have a 3. So we're going to write y to the power of n. No, not n. I'm going to write 9 minus k. And it's not a y, it is a 3. So we'll put a 3 there. And then if we look at our sum, the k equals 0 term is going to have a 2x to the k. When you multiply that out, that's an x to the k and x to the 0. So that won't have an x to the 5. So the term with an x to the 5th in it is the k equals 0 term. Not the k equals 0 term. What am I writing? The k equals 5 term, which we know what the k equals 0 5 term is. That is 9 choose 5, and then 2x to the 5th, 3 to the 9 minus 5, which we can simplify down to 9 factorial over 5 factorial, 4 factorial, and then 2 to the 5th, x to the 5th, and then 3 to the 4th. And so the coefficient, which is just the number attached to the x to the 5th, is that expression 9 factorial over 5 factorial, 4 factorial, times 2 to the 5th, times 3 to the 4th. And you can type that into your calculator if you're interested. All right. I want to say a little bit more about the variable k that's showing up in the binomial theorem. And I think this will be a little bit clearer if I write this out with everything being as concrete as possible. So I'm going to pick the numbers 4, 5, and 7. 4 plus 5 to the 7th by the binomial theorem, that is the sum from k equals 0 to 7. 7 choose k, 4 to the power of k, and 5 to the power of 7 minus k. And then k is what we call a dummy variable. It is the variable that shows up in a for loop. The variable that's not allowed to mean, anything else that you care about. it tells you where in the sum you are. There's no k showing up on our right hand side. So in a sense, the k doesn't really mean anything. It doesn't correspond to anything physical and concrete. So if we expand this out, we get the 7 choose 0, 4 to the 0, 5 to the 7. And then we get the 7 choose 1, 4 to the 1, 5 to the 6 term. And so on. And I think I'll stop there. I'm getting bored. But my point is, this is the k equals 0 piece. The k equals 1 piece. The k equals 2 piece, and so on. But the k isn't referring to anything real. It's just letting you keep track of what's going on in the sum. And I want to emphasize, you're never going to solve for your k, your variables of summation, because you see this expression we've got, k equals 0, k equals 1, 2, 3, 4, 5, 6, 7. You aren't going to have one k value. So the k variable, the variable of summation, is sometimes kind of a squishy thing. You can think of it as the for loop variable. It's really how you should think of it, but it's it can be a little bit confusing to think about in general.